In this video, I'll be explaining one of my projects while building a GPIO driver. So in this project, we'll be blinking the onboard LED, which is over here. So let's build a simple project for that. Here I have built two files here, that is a header file for GPIO and GPIO driver.c file, and a general header file here. In our project, to blink an LED, here is the code. Here I have created a function to provide a software delay. Here I have created a handler structure called the variable name is GPIO LED. And if you want to see what's inside the handler structure, let's explore that also. The handler structure has two structures in that. One is register definition structure and one is pin configuration structure. So whatever we need, our requirements or what we wish to set our pin as will be stored in the pin configuration structure. The details of the pin configuration structure is above here itself. So inside the structure we will be giving pin number, pin mode, pin speed, pull up, pull down, and output type, alternate function mode. And in GPIO register definition, the general registers will be there, and I can show that also. Yeah, this is the GPIO register definition structure. So this is directly taken from the reference manual, and instead of creating different variables for each registers, I have just created a structure, and which gives me an as you all know the properties of structure, it gives an incremental address which helps me to give the offset for each register. So let's get back to the program here, and I have created a variable called GPIO LED by using my and first thing is I'll be initializing it to the base address of the GPIO A port, and later I'll be configuring all my needs to the GPIO pin config structure members. So my user LED, this thing is just connected to the PA5 port, and you can see that from the schematic here. This is the LD2 green and this is connected to the PA5 port. So I need to configure the PA5 pin in port A registers. So let's do that. The pin number is 5 and I'm setting it as the output mode, and the output type will be push-pull configuration because I don't want to use open drain configuration. There are two configurations. If you want I can show that also, and I'll be showing that. Wait for a minute. These are the different configurations which you can set your GPIO for, and this is a circuit here. So here I'll be in the output driver type, and I need both PMOS and NMOS, and PMOS to pull up the line to VDD and NMOS to pull down the line to the ground. So I'll be using the push pull. In open drain we'll just not have the PMOS here, we'll only have NMOS. So you need to connect external pull up resistors to pull the output line to high. So that was about the pin output type, that is push pull, and the speed is here is medium. We can set the GPIO pins to different speeds. All GPIO registers are 32-bit registers, and these are the different bit values which you need to do to set it to different speeds. And the next thing is pull up or pull down registers. So I don't need any pull up or pull down registers as I am already in the push pull mode. So I am not using any push pull pull up or pull down registers. So I have created all the macros which I am using here. I can show you that. In the header file of GPIO we have n number of macros which will be using in the applications. So these are the registers. In the main header file also we have many macros which we have done. So next, in this is the GPIO init API function. By calling this function we'll be initializing the GPIO. In this initialization we'll be just giving clocks to the GPIO port A, and we will be configuring all the registers which was in the config register. So I'll be showing you that. So the first register, first function which will be called is the peripheral clock enable register. So this is the peripheral clock enable registers. We'll be enabling the clock through RCC PHB1 enable register. And after enabling the clock for GPIO A, then the next thing what we will be doing is configuring the registers inside the GPIO A port. So this all is that part. Then we'll be setting the speed, then pull up, pull down, output type, and if you are using alternate functionality, then that. This is the deinitialization, and this is to read the input pin, and this is to write into the output pin. And in this example we'll be using this itself. So by using another API, that is the output write function, we'll be setting the pin to high, and after a delay we'll be setting it to low, and again there will be delay to see the LED is turned off. So by looping into this, we'll be just turning on and off, and this is just blinking an LED. So this is my board, and so now let's run the program. So now let's run the program. And it's into the debugging mode. As you can see, the LED is blinking. This was all about the LED blinking project by using our own drivers. So let's jump into the next project. In this video, or in this project, we'll be using both GPIO pins for input and output modes. This push button will be used as input and LED will be used as output. So whenever I press this button, LED must be turned on. So in this project we'll be doing that. So let's see at the code. And this is the code, and it's exactly similar to the previous one. Here I have created two structures, one for GPIO LED and GPIO button. So let's look in the schematic and gain some information about the ports to which LED and the push button is connected to. As you all know, previously I showed you the LED is connected to the PF5. So now let's look into the push button where it's connected, and this is our push button. Come on, focus, bro. Yeah, this is my push button, and this thing is connected to the PC13. So this will be always connected to the VDT. Whenever I press this button, this will be connected to the ground and will be read as 0. So initially it will be high. Whenever I press this button, it will be read as low. So let's code it accordingly. So this is an polling method. I haven't used interrupt till now, and we'll be learning interrupt in our next project. So this is first we'll be reading the pin, that is the push button pin, which I have configured as input mode here, and I'll be not using any push pull or pull up or pull down register, as my push button already has an pull up and pull up register. So I'll not be using any of them here. So whenever the pin is read as high, the LED will be reset, and whenever it's read as low, the LED will be set. And let's see at the output here. I'm trying to focus. Yeah. So whenever I press this, the LED will be turned on. Whenever I release this, LED will be turned off. And this is an polling method, so it's wasting much of the energy of the microcontroller. Microcontroller is always in this while loop, searching for checking for the status of the push button. So to improvise this, we must use interrupt method, so we can do some other tasks instead of just running into the while loop and just checking them. In this video, we'll be just improvising the previous project, that is using both the button and LED. In this project, we'll be using interrupts to control them. So this is the code for that. Here the same thing is done. I have created two handlers, that is GPIO button and LED, and instead of using a polling method which is here, I have used an interrupt handler to do the job. Okay, so in this project what will be happening is, whenever I press this button, an interrupt will be triggered and this handler function will be called, and based on the present state of the LED, the handler function will decide whether to turn on or off the LED. So it works just like this. Whenever I press this button, the interrupt will be called, and as LED was turned off, it will be turned on. Again, whenever I press this button, the interrupt will be triggered, and based on the present state, it will be inverted. So when I press this button, it gets turned off. Again, when I press it, it gets turned on. So let's explore how it works. The interrupt mechanism in Cortex-M is very different and it's a bit hard to learn. So let's explore one by one. So here the push button, that is this pin, is set into the mode that is called interrupt fault triggered. So by looking at the schematic, we can just understand that this thing will be always high. So whenever I press this button, it will be pulled down. So whenever I press the button, the falling edge will be appearing first. When I release the button, then again it will be unrising edge. So as we get the falling edge first, I have triggered this pin to be triggered for falling edge itself, and everything remains the same. Now let's look into the how the interrupt mechanism works in Cortex-M. So this is how. Directly we can't control the interrupt with nested vector interrupt controller. Before that, to control the GPIOs, we have another block that is called external interrupt controller. This block looks after all the things, that is rising edge, falling edge, other things. So let's explore them one by one. This is the vector table which is here. So we have different lines from EXTI going into the NVIC. From the EXTI block to the NVIC, we have different lines. From these lines, we just get triggered, and the NVIC pendant registers will be then processed by the core. So let's explore that. See, the interrupt number on the vector table will be EXTI 0 line, then EXTI 1, EXTI 2, EXTI 3, EXTI 4. Then the other from EXTI 5 to 9 is a banked line. We have all the EXTI 9 to 5 in one single line, and one more is EXTI 10 to 15. That is also a banked line. So by this we get to know that we have two banked lines in EXTI controller, and this is how EXTI line exactly looks like it's just act like a multiplexer. So we need to configure in EXTI 0 line which port 0th pin will be selected, and this can be selected by using system config register. This is a system config register, and there are 4 registers like this. So by writing into these bits, we can configure the which port, which pin is just going to be placed on each EXTI line. So if you want the PA port of a 0th pin in EXTI 0th, you need to write 0, and similarly the other configurations are written here. So we have around 4 system config registers. This was about the EXTI block, and here the major things which we need to do is, after when for example in the banked lines, there is no thing like all EXTI 9, 4 or 9, 5, 6, 8 can trigger the at a time simultaneously, and you wouldn't even get to know that which pin or which interrupt got triggered. So to find out that, inside interrupt handler you need to check the pending register of EXTI. So that will be this register. By checking into these registers, you can find out that in banked EXTI lines which of the interrupt line got triggered. By checking this pending registers, you can always do that, and you should always clear the EXTI pending registers by writing it to 1. and if you want to trigger it as a falling triggering, then you need to configure this register, or rising triggering, then you need to configure this register. Always you need to enable this interrupt. You should unmask the bits in this registers by writing it to 1. You can unmask the EXTI line. So as soon as the interrupt gets triggered and EXTI block processes it and detects the rising or falling edge which you have configured, this position or this interrupt will be triggered. By this we can just we will directly get into this handler, and you can get this handler. I have just written a default or I have just made another handler by using the weak function. I'll show. Go to the startup. You can see by default there are many weak functions which are created, and all they are have a default handler, that is infinite loop itself. So by just rewriting this, you can create another function handler. The compiler will take the handler which is written by you. So this is the handler here, and I have written according to the exercise which I showed you. And this was all about the interrupt mode. And this was all about the GPIO driver development, and even you can develop this driver. And do subscribe for more exciting projects, or I'll be coming up with many more drivers, be it SPI, UART and I2C also. Thank you.